Good morning, physics students. This is Mrs. Krumschreider, and this is your teaching video for your concept development practice page 4-1. Again, feel free to basically do your page as I do my page with you. So, trying to decide if it's better with or without the light here. And I don't think there's much difference, so we'll just leave it off. All right. Number 1 asks, Aunt Millie gives you $10 per second for 4 seconds. How much money do you have after 4 seconds? So the way I would prefer you do this is that 4 seconds and you get $10 per second. And so that's how you figure out that you should do 4 times 10, which is $40. And again, I would like you to show your work, please. Okay. Number 2, a ball dropped from rest picks up speed at 10 meters per second. After it falls for 4 seconds, how fast is it going? So again, same kind of thing, 4 seconds, it picks up 10 meters per second. So that gives us 40 meters. Number 3, you have $20 and Uncle Harry gives you $10 each second for 3 seconds. How much money do you have after 3 seconds? So again, for 3 seconds, he gives you $10 per second. So he's going to add $30 to what you already have, but you have to add what you already had, which was 20, so you end up with a total of $50. Number 4, a ball is thrown straight down with an initial speed of 20 meters per second. After 3 seconds, how fast is it going? Well, again, we can kind of do this that same way as we do. We know, remember, that G is our acceleration due to gravity, which is 10 meters per second squared. Okay. So we have 3 seconds, and the acceleration is 10 meters per second squared. So that means it picks up 30 meters per second of speed, but it was going 20 initially, so I have to add the 20 to it. So it's going to be going 50 meters per second. You have $50 and you pay Aunt Minnie $10 per second. When will your money run out? Right? So, again, I have $50, and this one might be easier just to kind of think about. But I have $50 and I'm going to pay $10 per second. So after 1 second, I have $40. After 2 seconds, I have 30. 3 seconds. So here's second 1, 2, 3, 4, 5 seconds. My money's going to run out in 5 seconds. You shoot an arrow straight up at 50 meters per second. When will it run out of speed? So this is that idea that, again, because gravity acts at 10 meters per second, and remember, it's always working or acting downward, that means that each second, it decreases the speed of an object that's moving upward by 10 meters per second. So if I'm starting at 50, after 1 second, it's going to be going 40 meters, then 30, then 20, then 10, and then 0 meters per second. So 1, 2, 3, 4, 5 seconds is when it's going to run out of speed. So what will the arrow speed 5 seconds? What will be the arrow speed 5 seconds after you shoot it? Well, we just figured that out, right? It's going to be 0 meters per second. What will its speed be 6 seconds after you shoot it and 7 seconds, right? So this is talking about this idea that as I shoot this, right, my arrow's going up, 2, 3, 4, 5, right? And at 5 seconds, it reaches its top. Now, what does it start to do? Well, it's going to start to fall back down, right? So at 6 seconds, right, this was 1, 2, 3, 4, 5. Here's 6 seconds. So what will be the arrow speed, so what will be its speed 6 seconds after you shoot it? Well, up here it was 0 meters per second. Now it's getting pulled back down by gravity. So it's going to have picked up 10 meters per second. So at 6 seconds, it's going to be moving 10 meters per second. After 7 seconds, it's going to pick up another 10 meters per second. So it'll be going 20 meters per second. So there's lots of different ways that you can answer these. Sometimes it's just easier to just kind of draw a picture and think about what's happening. All right, free fall distance. Speed is one thing, distance another. Where is the arrow you shoot up at 50 meters per second when it runs out of speed? So we already know that the time for this is 5 seconds. We answered that up here. So now we're going to use our equation, which is d equals 1/2 gt squared. So 0.5 times 10 meters per second squared times our time, which is 5 seconds, and then we square that. So on our calculator, we're going to do 0.5 times 10 times 5 squared. That tells us it's going to be 125 meters up in the air above where we shot it from. So if we kind of remember, this was kind of our picture, right? From wherever we started, here's our kind of arrow at 0 seconds. What this is saying is this distance here is 125 meters. So the arrow goes 125 meters up in the air. Now remember, in real life that wouldn't actually happen because we have air resistance, but we are ignoring air resistance to make our problems much simpler. So number 2, how high will the arrow be 7 seconds after being shot up at 50 meters per second? Okay. Well, remember, okay, that means we need to figure out in these 2 seconds here how much it's going to fall, okay? So we could do d equals 1/2 gt squared and use 2 seconds here because that's how long it's falling. So 0.5 times 10 meters per second squared times 2 seconds squared. 0.5 times 10 times 2 squared, okay, says it's 20 meters that it's going to fall, right? That's how far it's going to fall here. So how do we figure out its height? Well, we're going to have to take the 125 meters and subtract the 20 meters, which gives us 105 meters. So we subtracted that because we knew at 5 seconds the arrow had hit the peak of its height, and now it fell for 2 seconds. We figured out how far it would fall at that time, which was the 20 meters. So we subtract that from its maximum height to figure out how high it currently is. All right, Aunt Minnie drops a penny into a wishing well, and it falls for 3 seconds before hitting the water. How fast is it going when it hits? So again, I like it. Again, for physics, it's helpful sometimes to draw pictures. So I made it kind of look like a wish, or a cliff will make it look like a wishing well, right? So it's a well. At the bottom of the well, there's some water, okay? And we know that here our coin is starting, okay? And it's at 0 meters per second, it's resting. And we know that it's going to fall and hit this water. And we know that the time for that is 3 seconds. So we want to know how fast is it going. How fast, remember, is a question of velocity. So our equation for velocity, okay, is gt. So we plug in 10 meters per second squared times our 3 seconds, which gives us 30 meters per second. So that's telling us that the answer to this question here is 30 meters per second. And that should make sense to us, right? Because again, if we kind of reason through this the other way, in the first second, it picks up 10 meters per second of speed. Another 10 meters per second, so it's going 20 at the end of 2 seconds. And another 10 meters of seconds, so it's going 30 at the end of 3 seconds. So when we're talking about like 3 seconds, it's not too bad to reason through that. But if we're talking about 15 seconds, it might be easier to use our equation. Part B. What is the penny's average speed during its 3-second drop? So remember to figure out our average, we'll just use AVG, our average speed or velocity. We use our first velocity plus our second velocity and divide it by 2. Our first velocity in this case is the 0 meters per second that it was at rest. Our second velocity is the 30 meters per second that we just calculated. Okay, so we put 0 meters per second plus 30 meters per second divided by 2. So 0 plus 30 is 30. 30 divided by 2 is 15 meters per second. So 15 meters per second. How far down is the water surface? So now, how far down is asking us about distance. And remember, our equation for distance is 1/2 gt squared. So 0.5, 10 meters per second squared, times our time, which was 3 seconds squared. So again, I put that in my calculator. And 0.5 times 10 times 3 squared is 45 meters. So how far down is that water? It is 45 meters. So I would encourage you, again, maybe on a separate sheet of paper, or if you've printed this on the back side of your paper, or if you're handwriting it, just put it with this problem. But here's the work for how you do that. Having your work can be helpful because on a homework assignment, if you're asked to solve a similar problem, you can look back at the work and figure out how you did it. If all you have is an answer and you don't remember how you did it, it doesn't help you remember how to do it. Same thing if a test or quiz, right? You get to use your notes. So if you have this written down like this and you have a similar question on a test or quiz, then it might help you remember how to do it. All right, Aunt Minnie didn't get her wish, so she goes to a deeper wishing well and throws a penny straight down into it at 10 meters per second. How far does the penny go in 3 seconds? So, similar situation, right? But my little object here, this time its initial velocity is 10 meters per second because it tells us that she throws it and it's starting with 10 meters per second. It's still going to fall and hit our water, okay, and it still takes 3 seconds. So we can use some of the same math that we already did, right? The velocity that it's going to pick up is still gt, which is still 10 meters per second squared times 3 seconds, which is 30 meters per second. The difference is, this time, it didn't start at rest. So to figure out my final velocity here, I have to take the 30 meters per second that it picks up and add to it the 10 meters per second that it had when it started. So my final velocity this time is 40 meters per second. Okay. Now, it doesn't ask about average, right? It really just asks how far does this penny go in 3 seconds. So, to do that, we have to figure out its distance. So our distance is 1/2 gt squared, which is 1/2 r10 All right, so sorry. That second question asks, how far does this penny go in 3 seconds? Because it has an initial velocity and now we know its final velocity, we want to actually figure out its average velocity during that fall. So we're going to take our first velocity plus our second velocity and divide it by 2. Our first velocity in this case was the 10 meters per second. The second velocity was the 40 meters per second, and we're going to divide that by 2, which tells us our average velocity during that fall was 50 divided by 2, 25 meters per second. Now, that's the average velocity. So to figure out how far it falls, our distance is going to be our average velocity times our time. And this is different, okay, than how we did this one, because this one assumed you were not moving. We have to add the fact that we're moving when we start, okay? That there's velocity initially. So we're going to take our 25 meters per second, which is on average how fast we fall, and the fact that we fall for 3 seconds, which gives us 75 meters. So how far does this penny go in 3 seconds? It's 75 meters. So that is that first page of that. All right, straight up and straight down. The sketch is similar to figure 4.9 in the textbook. Assume negligible air resistance and g equals 10 meters per second squared. Table 1 shows the velocity data, okay, for the figure for t equals 0 to t equals 8 seconds. Complete this table. Distances traveled are from the starting point, the displacements. Okay. Table 2 is for the greater initial velocity. Complete it. Table 3 doesn't specify an initial velocity. Choose your own and complete the table accordingly. Choosing up as plus and down as negative, v equals v0 minus gt, then falling from rest, v0 equals 0. V equals negative gt. Okay, so time in seconds and our distance, right? So distance is 1/2 gt squared. Okay. So when time equals 1, we can just, again, we're going to kind of plug into this. So we have 0.5 times 10 meters per second squared times our time every time squared. So that's one way we could do it. honestly, I think it might be easier to do it a little bit different way, to do it more using that averages this time. So let's take a look at that, okay? So we can figure out our average velocity here by adding these two up. So 30 plus 20 is 50 divided by 2. So what I'm going to do here, this means we're taking our velocity 1 plus our velocity 2 and dividing it by 2 each time. So 30 plus 20 is 50 divided by 2 is 25. So this is our average velocity over here. So on average, it falls 25 meters per second, and it falls for 1 second. So to figure out my distance then, okay, then my distance is my average velocity times my time. And my time each time is just going to be 1 additional second. So it's going to be 25 meters here, because it's 25 meters per second times 1 second. So here, 20 plus 10 divided by 2 is 15 meters per second times 1 second. So it's going to go an additional 15 meters. So it's going to go 25 plus 15, which gives me a total of 40 meters. Ten plus 0 divided by 2, right? Oops. 10 plus 0 is 10 divided by 2 should be 5. How did I get? Okay. 5 meters per second. So it's going to go the 40 it already has plus another 5, which gives us 45 meters. Now, it starts to come down, right? So it's 0 and 10. And we can even use the negative 10. 0 plus a negative 10 divided by 2 is minus 5 meters per second. Okay, so that means times 1 means I'm going to take my 45 meters and I'm going to subtract 5, which gives me 40 meters. Now, that makes sense based on our picture, because notice here, each time as we're falling, we're at that same distance. So I should kind of expect my distances to continue to be the same. So I have negative 10 plus a negative 20 divided by 2 gives me minus 15 meters per second. So I take the 40, I subtract 15. 40 minus 15 is 25 meters. Negative 20 plus negative 30 divided by 2 gives me, it falls 25 meters per second on average, times the 1 second means I'm starting at 25 and I'm going to subtract 25, which gives me 0 meters, which means at time 6 seconds it's back where it started, which is consistent with this picture here. Negative 30 plus negative 40 divided by 2, negative 35. So it falls 35 meters per second times the 1 second, right, which is negative 35. So I start at 0, I subtract 35, and so I get minus 35 meters. Now, all that minus means is it's 35 meters below where we started. Next, negative 40 plus a negative 50 divided by 2 is it fell 45 more meters per second for 1 second. So I start with my negative 35 and I subtract 45. Okay. So negative 35 subtract 45 gives me negative 80 meters. All right, our second one. First thing we have to do is fill in our velocity. To fill in our velocities, we have to remember that gravity is going to cause us to lose 10 meters per second for every second. So here we're 40. Our next speed's going to be 30, then 20, then 0, and then again, or sorry, not from 20 to 0, 20 to 10, and then 0, and then we're going to pick up because now we're starting to fall back down, 10, 20, 30, 40. And then we can do this the same way, right? So my average here is going to be 40 plus 30, which is 70 divided by 2, which is 35 meters per second. 25 meters per second, right? There's kind of a pattern here. 15 meters per second. 5 meters per second. So I'm just kind of doing all my averages. This is going to be 5 meters per second. Okay. And we can kind of say these are negative, right? Because these are velocities going down. So this will be a negative 5 meters per second, a negative 15 meters per second, a negative 25 meters per second is our average, and a negative 35 meters per second. So 35 meters per second on average times, I'm using this equation again, times our time, which is 1 second. So we're going to go up 35 meters. 25 meters per second times 1 second. So we're going to take our 35 and add the 25 more meters that we climb. So we're at 60 meters. Here, again, 15 meters per second on average times 1 second means 15 meters. So again, we're going to take our 60 that we're already at, and we're going to add 15 more meters to it. So that takes us to 75 meters. Next, 5 meters per second times 1 second means we're going to go up 5 more meters. So we're at 75, we're going to add 5, and so now we're at 80 meters. Now we're at our top. We know we're at our top because we're at that moment of having no velocity. So now we're going to start to fall back down. So again, our average is minus a negative 5 meters per second times 1 second. So I'm going to start at my 80 and I'm going to subtract 5 this time. So I'm at 75 meters. Now remember, I expect these distances to match. Okay? But again, we'll kind of prove it, right? So here my average speed is negative 15 meters per second. So I'm starting at 75, I'm subtracting 15, which takes me to 60 meters. My next second of fall, my average is negative 25 meters per second times 1 second. So I'm starting at 60 and I'm going to lose 25 meters. So that is going to take me to 60 minus 25 is 35 meters. And again, I expect it to match, which makes sense. Next, average of negative 35 meters per second times 1 second. So I'm starting at 35 and I'm going to subtract the 35. And so now I'm back at my 0 meters. Notice also my velocities are the same. The difference is here my object is moving upwards. That's why it's positive. And here my object is moving downwards, which is why my velocity is negative. Because remember, velocity is a vector quantity and requires a direction. So for number 3, you can pick whatever you would like for a number. I'm going to use, let's do 20. That's kind of in between this, right? So then it's going to be going 10, 0, negative 10, because it'll be falling down, negative 20, negative 30, negative 40, negative 50, and negative 60. Again, if I do my averages here, this is a positive 15 meters per second. This is going to be a positive 5 meters per second. This is going to be a negative 5 meters per second. This is a negative 15 meters per second. And again, you can do this, if you have to do the math, there's nothing wrong with that, right? I just do negative 20 plus negative 50, or 30, which is negative 50 divided by 2, is a negative 25 meters per second. If you see the pattern, that's great too. So 15 meters per second. Okay, so I'm starting at my 0. I'm going to add 15, so I'm at 15 meters here. I'm at my 15. I'm going to add 5 for then it goes up, so now I'm at 20 meters. Now I'm losing that 5, so 20 minus the 5 takes me back to the 15 meters. I'm at 15 and I lose 15, so that takes me to 0 meters. Starting at 0, I'm going to lose 25 meters of height, so I'm at minus 25. Now remember, minus 25 just means I'm 25 meters below where I started. Okay, so I'm kind of falling below that cliff now. I'm starting at negative 25. I'm going to lose another 35. Okay, so I'm at negative 60 meters. I'm at negative 60. I'm going to lose another 45. So now I'm at negative 105 meters. And again, I'm starting at negative 105 and I'm losing another 55. So I'm at negative 160 meters. Excuse me for a moment. I have to let my dog out. So again here, you can put in anyone. If you want to choose something different here, that's perfectly fine. But this again is just kind of showing you how things go up and go down. And again, the thing to notice here is kind of that mirroring part here, right? And after we get our peak, right, these speeds match and these distances, these heights match as well. So that's why this looks the way it does, okay? And this is a way where you actually could answer this question without doing math, right? Because a question might be, you throw a ball in the air starting at 30 meters per second. How fast is the ball moving when it returns to your hand? Well, it's moving 30 meters per second because it's going to have lost its speed as it went up, and then it picks up the same amount of speed as it comes down, which means it returns to your hand at the same speed. So it makes it possible to answer a question like that without doing math. You could just say, because it's going to gain, because the acceleration due to gravity stays constant, it's going to gain speed or lose speed at the same rate that it gains speed when it's falling back down, so it will return to my hand at the same speed. Okay, so again, it kind of allows you to kind of cheat, if you will, a little bit when you answer a question like that. So next we have free fall. A rock dropped from the top of a cliff picks up speed as it falls. Pretend that a speedometer and odometer are attached to the rock to show readings of speed and distance at 1 second intervals. Most speed and distance are 0 at time 0. See the sketch, right? So they're just saying time 0, it's not moving. Note that after falling 1 second, the speed reading is 10 meters per second and the distance fallen is 5 meters. The readings for succeeding seconds of fall are not shown and are left for you to complete. Draw the position of the speedometer pointer and write in the correct odometer reading for each time. Use G equals 10 meters per second squared and neglect air resistance. So they give you these equations, which is fine, okay? So Again, how do we know it's fallen 5 seconds? We can, or 5 meters. Oops, sorry. I hear my dog scratching to come back in. Come right. So how do we get the 5 meters? So we can use the 0.5 times 10 times 1 squared, which is 5. So that's where the distance came from. The speed, okay, is from the v equals gt, so that's the 10 times 1, which is 10. I think that one, rather than doing it with a calculator, is just easier. So let's fill these in, right? At time equals 2, it's going to have picked up 10 meters per second, so now it's going to be going 20 meters. Now it's going to be going 30 meters. Now it's going to be going 40 meters. Now it's going to be going 50 meters. And lastly, it's going to be going 60 meters. Okay, so 60 meters per second, 50 meters per second, 40 meters per second, 30 meters per second. And again, this is probably just easier doing without doing math because we're increasing by 1 second intervals, and we know that because our gravity is 10 meters per second squared, we're going to pick up 10 meters of second of speed each second that we fall. Now, to do the distances then, we can use our calculator. Okay, so again, our equation is, trying to kind of get it all in here, our equation is this one. So we have 0.5 times 10 times, and at 2 seconds, 2 squared, gives us 20 meters. Our next one is 3 seconds, so 0.5 times 10 times 3 squared is 45 meters. 0.5 times 10 times 4 squared is 80 meters. 0.5 times 10 times 5 squared is 125 meters. 0.5 times 10 times 6 squared is 180 meters. Okay, so that's how we do those calculations. So now we can look at these questions. The speedometer reading increased by the same amount, which we've talked about, the 10 meters per second each second. This increase in speed per second is called, that's acceleration. In this case, right, it's due to gravity because we're just falling. The distance fallen increases as the square of, right? So it's saying in this equation, our distance fallen increases as a square of, so it's asking what gets squared? Time. Right? Time is what is squared in that equation. If it takes 7 seconds to reach the ground, then its speed at impact is, and again, I can do the v equals gt. Speed is asking about our velocity, so it's our v equals gt, which is our 10 meters per second squared times our 7 seconds, right, which is 70 meters per second. The total distance fallen, that's going to be the d equals 1/2 10 meters per second squared times the 7 seconds squared. So 0.5 times 10 times 7 squared, 245 meters. And its acceleration of fall just before impact is, acceleration, remember, gravity isn't changing. So the acceleration is still 10 meters per second squared. So this is that because gravity doesn't change, So the acceleration is constant or unchanging. Okay, so there is that page. All right, on to our last page, non-accelerated motion. The sketch shows a ball rolling at constant velocity along a level floor. The ball rolls from the first position shown to the second in 1 second. The two positions are 1 meter apart. Sketch the ball at successive 1 second intervals all the way to the wall. Neglect resistance. It's going to be helpful to have a ruler. So here's my ruler. I can kind of measure this. This is really about 1 inch. So that means because it's constant, they're going to be at 1 inch intervals. Okay, so here's my next one. Here's my next one. Here's my next one. And there's my last one. So here's my ball again. Here's my ball again. Here's my ball again. Here's my ball at the end. Okay, so I've done my sketching, right? So this is going to be, each time too, this distance is going to be 1 meter. This is still 1 meter. This is still 1 meter. And the reason for this is sort of that same reason that it was always 10 meters per second that we changed our speed, because this is constant. So did you draw successive ball positions evenly spaced, farther apart or closer together, and why? Well, we drew them evenly spaced because the ball is moving at constant velocity. So that means it moves equal distances in the same amount of time. So the ball reaches the wall with a speed of, okay, well, again, it's moving, its speed, right? Our equation for speed is our change in distance over our change in time. What distance does it move? It moves 1 meter, and in what amount of time? 1 second. So its speed is 1 meter per second. And it takes a time up. So they're asking, how long does it take to reach the wall? So here's 1 second, 2, 3, 4, 5. So it's going to take 5 seconds to reach the wall. Table 1 shows data for sprinting speeds of some animals. Make whatever computations are necessary to complete this. So again, speed equals change in distance over change in time. If I'm asked to solve for distance, remember distance is going to be speed times change in time, or my time. And if I'm asked for time, time is going to be distance divided by speed. So, doing these calculations, for the greyhound, we're missing our speed, so we're going to use this equation here. So my distance is 160 meters divided by my time of 10. So that's 16 meters per second. For my gazelle, notice my times are a little bit different. It's going to be in hours. My time is my distance, which is 1 kilometer, divided by my speed, which is 100 kilometers per hour. So my time is 0.01 hours this time. And my turtle, I'm looking for my distance. So that's going to be my speed, which is 1 centimeter per second, times my time, which is 30. So that's going to be 30. And notice the units this time are going to be centimeters because my distance is measured in centimeters. So that's just some calculations using those equations. Number 3. An object starting from rest gains a speed, velocity equals acceleration times time, when it undergoes uniform acceleration. The distance covered is distance equals 1/2 at squared. Uniform acceleration occurs for a ball rolling down an inclined plane. The plane below is tilted, so a ball picks up a speed of 2 meters per second each second. Then its acceleration is 2 meters per second squared. The positions of the ball are shown for 1 second intervals. Complete the 6 blank spaces for the distance covered and the 4 blanks for speeds. So we can do the distances first, right? So we're using this distance equals 1/2 at squared. So 0.5, our a this time is the 2 meters per second squared. So this isn't free fall, so I have to use a different acceleration. And then we'll just put our time in, okay, and square it. So they told us that these are successive pictures at 1 second intervals. So I can kind of put it here that this is my time equals 1 second. Here my time equals 2 seconds. Here my time equals 3 seconds. Here my time equals 4 seconds. And here my time equals 5 seconds. So to figure out my distances, okay, we can just kind of check 0.5 times 2 times 1 squared is the 1 meter that we see right here. So I want to check this 4 meter one. That's at 2 seconds. 0.5 times 2 times 2 squared is 4 meters. That's where the 4 meters came from. So now we're asked to figure this out for 3 seconds. So 0.5 times 2 times 3 squared is 9 meters. So right here, this is 9 meters. So this next one, 0.5 times 2 times 4 squared is 16 meters. And we'll just check this 25, right? 0.5 times 2 times 5 squared is 25 meters. So we filled in all of those distances. Now we're also asked to fill in our velocities, and our velocities are our AT. This time our acceleration is still the 2 meters per second squared, and then we'll multiply that by the t. So again, let's see where we got the 2 for this first time, right? 2 times 1 second is 2. Next we have 2 seconds, so 2 times 2 is 4. So here's moving 4 meters per second. Next we have 3 seconds, so 2 times 3 is 6 meters per second. And notice, right, we're picking up 2 meters per second of speed each time. So I can do the math, right? 2 times 4 is 8 meters per second. Or I could just add 2. So this one over here is going to be 10 meters per second. Now, there are a couple distances missing here, right? So notice, I have 1 meter, and so how far did it go just in this second? Well, my total's 4, so this has to be 3 meters. So this one here, right, I have 4, the total's 9, so 9 minus 4 is, this one here is 5 meters. Here, my total is 16 meters, minus 9 means 7 meters. And lastly, I have 25 minus 16, okay, which leaves me 9 meters. So we filled in all that they've asked. So it says, do you see that the total distance from the starting point increases as the square of the time? Well, yes, we do from the equation. This was discovered by Galileo. If the incline were to continue, predict the ball's distance from the starting point for the next 3 seconds. So basically it's saying if my time was 6 seconds, what would my distance be? So I still do my d equals 1/2 at squared. Okay, so 0.5 times 2 times 6 squared. It would be, my distance would be 36 meters. If my time equals 7 seconds, 0.5 times 2 times 7 squared, my distance is 49 meters. If my time equals 8 seconds, 0.5 times 2 times 8 squared, my distance is 64 meters. Okay, so all we did here again was we used this equation. Note the increase of distance between ball positions with time. Do you see an odd integer pattern also discovered by Galileo for this increase? So what they're talking about here is 1, 3, 5, 7, 9, here it's 11, 13, 15. If the incline were to continue, predict the successive distances between ball positions for the next 3 seconds, right? So yes, and we just kind of did that, right? We were at 9, so the next one would increase by 11 meters, then 13 meters, then 15 meters. So that is the end of that CDP. If you've done this along with me, then again, just scan it or take pictures of it and upload it for the assignment in Google Classroom, and you're all set to go. Have a great day. I'll talk to you tomorrow.